Welcome. Here are a few slides from the final review. They are slightly beefed up. First, a few definitions. We do calculus on a finite graph. There are nodes and connections, and also complete subgraphs like triangles play an important role. The gradient operation gets from a zero form, which is a function on vertices, a function on edges. It's straightforward. So get the value at an arrow, we just take the endpoint and we subtract the initial point. So for example, the arrow which goes from 2 to 6, we take 6 minus 2 and we attach to that arrow the value 4. So this is the value, this is the gradient value at that edge. And so on. We do that for every edge. So here's an example. We have a graph with 5 nodes, and we can now compute the gradient. For example, to the very right, 7, we have to add minus 2 to get to 5, and we can do that at every point. And this f, that is our gradient. That's a discrete analog of a vector field. Then we have the curl, which gets us from a one form, two form. Two form is a function on triangles. So I call f the one form. That's a function on the edges. And in order to get the function of the triangle, we just go along the triangle and add up all the f values. For example, in the left triangle here, we have 4 plus 3 minus 5. That's the value for that triangle x. That's df of x. And on the right-hand side, the orientation of the triangle is different. So we have 5 minus 3 minus 4. So that's just the opposite value. So here's an example, a larger graph. It's kind of a two-dimensional region, discrete region. If you want to compute the curl in every triangle. Here, if you don't say anything, the triangles are oriented counterclockwise. So here are the values of the curl. Then we have the dual gradient, which goes from one forms back to zero forms. It's kind of, you think about it as a divergence. To get a value at the point, we take all f values from edges which come in and subtract everything which goes out. So here in the example, we have a vertex x, and there is a value 4 coming in, a value 3 coming in, a value 6 going out. And we add that all up, we get the value 1. So that's d star f. And what is nice is these values all add up to 0. That's a conservation law, which already Kirchhoff has found. So here in this case, we have computed the d star f values, and if you add them up, you get 0. And then we have the dual curl, which goes from two forms to one form. It attaches to an edge just all the values of triangles, where triangles are added if they match the orientation and subtracted if they don't match the orientation. So in this case, for example, the edge x. So we have the 3 matches here. The triangle to the left matches. So we have 3, and to the left it doesn't match. So it's 3 minus 5. It's minus 2 is the value at the edge x. And then we have the zero form Laplacian. That's the discrete analog of the usual Laplacian. It's divergence of the gradient. So we have here an example of a function, a scalar function on the vertices. We can form this d star d, which first we form df, which is a vector field, a gradient field. And that's indicated here. And then we compute this divergence, and then we get the LF. That's also called the Kirchhoff, the matrix L. If you write it down as a matrix, it's called the Kirchhoff matrix. So that's the value which we have. But it's a divergence of the gradient like in the continuum. And then we have seen the one form Laplacian, which is Laplacians on vector, on one forms. And there it's a little bit more complicated because we can go down first and then up again, or first up and then down again. So in this case, we have this function given on the graph. I compute first d star f, which is a function on the vertices. This is kind of this divergence. And then we can use this and find the gradient. So this is d star. That's again a function on the again a function on the edges, again a one form. And then we have also to add the other, we go the other way. We first compute df, which is the curl. That's a function on the triangles. It's already written in. And then we go back to the vector field by just summing up the triangle values, and then we have the d star df. And the Laplacian value is d star plus d star d. In this case, on the right, it would be 6 minus 1. That would be the value of the edge at the very right. So that's the one form Laplacian. And then we have seen some integral theorems. All the integral theorems hold. It's almost trivial, but in this case we have a fundamental theorem of line integrals. So this is we have a gradient field. This actually has to be a gradient field in order that it works. And so we want to compute the line integral from A to B. So we can compute the line integral, which is 3 plus 3 plus 3 plus 1 minus 2. That's one possibility. Or we can just evaluate the function. So here's the function given on the vertices, which is a scalar function which has this vector field as a gradient, and then we have fb minus fa. So that's the same value. That's the fundamental theorem of line integrals. And then we have also seen Stokes theorem, Green's theorem. So it's here the same. So this graph could be embedded in a larger graph. So this is a surface. And we can compute the curl at every triangle, and we can compute also the line integral. So in this case, I computed the curl, and we can add that up. We can also add up the line integral. In this case, for the line integral, you have minus 3, minus 2, plus 2, plus 1, plus 2, plus 1, plus 2, minus 2. So you add that up, or you add up all the curls, and you get, in both cases, minus 2. So it's your turn. So it's another example you can try out. So first, the line integral. We can compute the line integral. We go counterclockwise around. So we start here at the left bottom, and then we have a minus 2, and then minus 1 and 1 cancel. So we are still minus 2. Then we subtract minus 1. So we have minus 1. And then we add 4, which is 3, and then subtract 2. This is 1. So the value is 1. And we could also do that with a curl. We can compute the curl values, which are indicated here, and add up all these curl values, and also these curl values add up to 1. That's the Stokes or Green theorem. And that's the end.